So we finished last time with a discussion of block diagrams and finally signal flow graphs, and we put down the direct form for a direct form 1 actually signal flow graph to implement a difference equation filter. Well, this is a direct implementation of the filter as factored with h of z is equal to h of p of z having the poles and hz of z having the zeros. And so when we multiply that by x on the right, then we filter with hz of z first, which is there, and hp of z second, which is there. But there's nothing that says we have to do it in that order. In fact, there might be compelling reasons to do it in another order. So if we were to flip this around, we're going to get another filter form, which is going to evolve into what we call direct form 2. Direct form 2 has the two sections simply reversed. We now have h p of z on the left and h z of z on the right. And because now the intermediate term is the one that's filtered with the all poles 0 instead of the all 0 filter, we'll give it a different name and we'll call this w of n. Other than that, everything is essentially the same. But one of the beauties of this is, look, the signal right here and right here, the two green highlighted points, is the same. It's wz of n. And that same filter is being delayed as part of the hp of z filtering, and it's being delayed as part of the hz of z filtering. So that means that this blue point and this blue point have the same value, as well as this magenta point and that magenta point. Well, since they're all the same values, and we're using memory to implement them, we could make this whole thing a little bit more efficient by squishing those two filters together and just using one delay chain instead of two identical delay chains. So we call this result direct form 2. And direct form 2 is obviously a little bit more efficient in terms of its memory usage. We only have 2 delays instead of the previous 4. It's very common to use direct form 2 in actual implementation. We'll talk about reasons, though, why we might want to try something different. So let's explore some other forms that can happen. These other forms don't come so much from manipulating the Z transform factoring as they come from graph theory. And these are called the transposed forms. You obtain a transposed form with the following 3 steps. 1, change the direction of every arrow. 2, swap the input and the output. 3, turn splitters into adders and adders into splitters. That's it. So let's see what this would look like. If we were to take our direct form 2 implementation that we just saw, or just made, put it down here and give ourselves a little bit of room, we are now going to change our x to a y and our y to an x. we'll change the direction on these, and the direction on those, and the direction on those. So rewriting this to make it a little bit neater and flipping it around now so that the X is on the left side as we're used to seeing. We have that this signal comes down, is multiplied by B0, B1, and B2. It's delayed, summed, delayed, and summed. And likewise, we take the output, we multiply it by A1 and A2, delay and sum, to get our Y of n. Scooting this over just a bit, because when you print OneNote documents, if it's too close to the edge of the bottom, OneNote will sometimes try to throw it onto another page. Okay, so this is called the Direct Form 2 Transposed filter. So why would we want this? This is actually, there are some advantages and some disadvantages to this. But there are some big advantages that are suggested by the fact that MATLAB implements this form. So, one disadvantage is the adders are now 3-element adders. We're adding 3 things instead of 2. However, there's only 2 of these adders, so maybe that's worth it. Each of those adders needs to be implemented typically as 2 cascaded adders, adding up the first 2 terms. And actually, I misspoke, not each of them. The middle adder takes in 3 inputs. The other 2 adders take in only 2 inputs each. So that's not too bad. So we have this 3-input adder that has to be implemented with 2 adders in series. It's not a problem. But here's something that's pretty cool. When you get a new input sample, you immediately multiply it by B0, B1, B2, and you're done with that input sample. From an implementation point of view, this is really nice. When you get your next sample, you multiply it by all these things, and you can ignore it, throw it away. We don't have to keep sample memory for the input samples. The same comes when we get our output. We multiply it by A1 and A2 respectively, and then send it out the door. Another advantage is we still have to have memories, 2 of these memories. It's no more memory efficient than the Direct Form 2. It is more memory efficient than the Direct Form 1. And here's the big advantage. Not only is it more memory efficient than Direct Form 1, it has the wonderful advantage that it processes the zeros first and the poles second. So why does this matter? Well, a pole will tend to amplify a signal hugely, and a zero, of course, will take it down to 0. If you have something that's maybe running up with, in fixed point or finite precision of some form or other, and basically anything in a digital system has finite precision, then causing it to blow up first might cause it to saturate, at which point bringing in the 0 will never fix anything. The damage has been done. By putting the zeros first, it brings it down, preventing saturation, then the pole could bring it back up. So an example of where this might matter would be a filter like this. I'm going to have to move these axes a little bit. They don't want to go. Well, let's pretend that we have good axes and keep going. There we are. And we put in our unit circle. There we go. If we had a pole there and a pole there, that's going to cause our signal to be amplified tremendously by those two poles. But if we're doing a notch filter, we would have a 0 there and a 0 there, at which point we would try to bring it back down. By doing the 0 first, then it prevents overflow from occurring in your filter. So this is just a minor implementation tweak that actually has some big impact in actual systems.